Today's lecture is about antiderivatives and indefinite integration. We are starting the integral portion of Calculus 1. We're going to start with antiderivatives, and that is partly a bridge to derivatives, but we're working our way to the fundamental theorem of calculus, which is the complete bridge between Calc 1 and Calc 2. First definition, as always, let a function f of x be given. An antiderivative of f of x is a function capital F, such that big F prime is equal to little f. So that means that an antiderivative is any function that when we take the derivative of it, we get the original function that was given. And then the set of all antiderivatives is the indefinite integral of f of x dx. And we get more than one because we know if we take the derivative of a constant, we get 0. So if we had something plus 1 or something plus 2, and the derivatives were the same, they would both be antiderivatives. All right, some examples. We're going to figure out which of the following in this list are antiderivatives of 10x squared plus 3x. So here, to find the answer, using only the definition that we need the derivative of the antiderivative is the original function, what we're going to do is we're just going to check the derivative of each of these functions that are given as possibilities and see which one is 10x squared plus 3x. Starting with 20x plus 3 plus c, the derivative of that will be 20, so that's not it. Moving on to 5x squared plus 3x plus c, the derivative of that will be 10x plus 3. Moving on to number 3, 10x cubed over 3 plus 3x squared plus over 2 plus c. When we take the derivative of that, we are going to get 10 times 3x squared over 3 plus 3 times 2x over 2, using constant multiple rules for derivatives there. And then we can do some cancellation. We get the 3's canceling in the first term, the 2's canceling in the second term, and that leaves us with 10x squared plus 3x. So that is an antiderivative of 10x squared plus 3x. And then if we check our last option, the derivative of 20x plus 3x squared plus c is 20 plus 6x, so it is not an antiderivative. Next example, we're going to figure out which of the following are antiderivatives of 12 times cosecant of 4x times secant of 4x. And again, we're just going to work our way through and take derivatives, starting with 3 tangent of natural log of 4x plus c. We're going to need the chain rule here. And we're going to get 3 times secant squared, that's from the derivative of tangent, natural log of 4x, that's leaving the inside part alone from the chain rule. Then we need the derivative of natural log of 4x, that's our 1 over 4x, but again, using the chain rule, we have to multiply by 4. That is not going to be our antiderivative. Second option, when we take the derivative, we're going to get 12 times 1 over 4x times 4 using the chain rule and the derivative of natural log. And then for the derivative of tangent of 4x, we're going to get 12 secant squared of 4x, and then we have to multiply by 4 from the chain rule. Not going to be our antiderivative again. Next one, we have 3 natural log of tangent of 4x. When we take the derivative of that, we're going to get 3 times 1 over tangent of 4x times secant squared of 4x, that's from the derivative of tangent, times 4, that's the derivative of 4x. That is a possibility still, doesn't look quite like it, but we'll move on and check the next one and come back if we need to. All right, 3 natural log of 4x plus 3 tangent of 4x. When we take the derivative, we're going to get 3 times 1 over 4x times 4. The derivative of tangent of 4x, or 3 tangent of 4x, we're going to get 3 secant squared of 4x times 4. That's definitely not going to be what we're looking for because we have that x in the denominator. So now we're going to go back to the 3 times 1 over tangent of 4x times secant squared of 4x times 4 and see what happens when we simplify. And when we do that, we can rewrite our tangent and secant in terms of sines and cosines. That's going to give us 3 cosine of 4x over sine of 4x. That's because the tangent is in the denominator, so we get the reciprocal, gives us cosine over sine. Times 1 over cosine squared of 4x, that's from the secant squared, because secant is 1 over cosine. So now we're going to cancel what we can. We've got a cosine that will cancel in numerator and denominator, so we can end up with 12 times 1 over sine of 4x times 1 over cosine of 4x, which is 12 cosecant of 4x times secant of 4x. So there's our antiderivative, is that third one there. And I think our last one of these types of examples, we're going to look at possible antiderivatives for 7x plus 14x natural log of 3x. And remember that for that 14x natural log of 3x, or any terms that are products like that, we need to use the product rule. So starting with 7x cubed natural log of 3x plus c, we take the derivative. We're going to get 21x squared natural log of 3x plus 7x cubed times 1 over 3x times 3. That's not what we're looking for because of that x squared with the 21. Next term, when we take the derivative, we get a 14x natural log of 3x plus 7x squared times 1 over 3x times 3. This is from the derivative of natural log of 3x. We'll come back to that. It's a possibility. Oh, no, we're going right ahead with that. Because we have the 14x natural log of 3x, which we've got right there, we want to see if we can simplify that second term. We've got an x that will cancel from the x squared and the x in the denominator. We can cancel the 3's, and that leaves us with 14x natural log of 3x plus 7x, which is the function we started with. So there, number 2 is an antiderivative. But checking our other terms just to be sure we don't get something else, taking the derivative in our next term, we get 7 natural log of 3x plus 7x times 1 over 3x times 3. Using the product rule, here is our derivative of 7x, here is our derivative of natural log of 3x. And then finally, we need the derivative of 7x squared plus natural log of 3x plus c, and we're going to get 14x plus 1 over 3x times 3 from that. So our antiderivative in that list was only the second option. All right, we have to talk about notation. This is a really important part of understanding what's happening here. All of this written out here says that the integral of f of x dx is equal to big F of x plus c. That's the way we would read that. And the way we identify all of the parts of that, this long stretched out integral sign here, that's called the integration symbol or integral sign. F of x, that original function that we're looking at, is called the integrand. Dx is called the differential of the differential of x. Big F of x, this is just one possible antiderivative because we know if we add different numbers to the end, when we take the derivative, that's just going to give us 0, so it's not going to be any different when we take the derivative. And then the plus c on the end, that c we call the constant of integration. And now we are ready for some more examples. And in these examples, we are going to be coming up with antiderivatives ourselves. In the first set of examples, I'm just going to flip back quickly. Right here, we were given some possibilities for the antiderivatives, and we just had to take the derivative of each one to figure out what was an antiderivative. This time, flipping back, we have to come up with the antiderivatives ourselves. So you should pause and watch the videos, fill in the examples, and then move on. All right, now we get to properties of indefinite integrals. I hope you enjoyed that series of examples. This theorem, 5.1.2 in your book, it's about derivatives and antiderivatives. And if you notice on the left-hand side, we have common derivative rules. And on the right-hand side, we have their corresponding indefinite integral rules. In other words, antiderivative rules is what we have on the right-hand side. So the first one, those are constant multiple rules. Second, those are sum and difference rules. Third, it's derivative and antiderivative of a constant in a way, involving 0 there. The derivative of x, the antiderivative of x. We have a power rule for derivatives and for antiderivatives. And notice here, and this is a really important thing, that the antiderivative power rule only applies when n is not equal to -1. That's because if you notice in the antiderivative rule, we get 1 over n plus 1. We don't want n to be -1 because then we would have 0 in the denominator, and that is something that is not defined. And then we have some rules involving the trig functions and how the derivatives of the trig functions relate to each other. And then number 12 I want to highlight here, the derivative of e to the x is e to the x. The antiderivative, the indefinite integral of e to the x dx is e to the x plus a constant for the antiderivative. And then for 1 over x, number 14 here, the integral of 1 over x dx gives us the natural log of absolute value of x plus c. Don't forget that absolute value. What we're going to do next is we are going to highlight some of those properties, and then we're going to look at examples using these properties. I definitely highly recommend that you have this table with you and that you're looking at it when you're working on examples and homework problems, because it will help you very much to have that reference list until you get really accomplished and get a lot of practice in, and then you won't need to look at the list so much anymore. All right, from that theorem, the first two properties give us two useful tools for working out integrals. The first property is a constant multiple property, and it allows us to pull constants out of the integral. The second property is the sum and difference property, and it allows us to separate integrals into individual terms. And then our example here at the end, we have the integral of negative 2x cubed plus 7e to the x, minus 5 sine of x plus 4 dx, which we can separate into negative 2 times the integral of x cubed dx, plus 7 times the integral of e to the x dx, minus 5 times the integral of sine of x plus 4 dx. And then we can apply the other rules in the theorem 5.12 in order to find antiderivatives of those individual terms. And this brings us to a whole series of examples. There are 18 of them. You can follow the link to see the video examples. All of them are in the same video, so it's long. Pause it as you need to, write everything down as you go. Of course, the very best approach would be for you to try and do these on your own, and then restart the video when you are ready for that next step to check your work, or if you just don't know what to do. And again, there are 18 of these, but go ahead and look at the videos, write these down, then go and do the homework. And there are all 18 examples, and you'll find them all on the video on YouTube.